it's time to start our last talk of the conference, and online talk is by Dr. Muhammad Zubair from University of Islamabad in Pakistan. He will talk us about ultracompact stars in the light of minimal geometry deformation. So please start. We now switch off our microphone in order to start with your presentation.
Okay, thank you so much. Okay, first of all, I would like to thank the organizing committee for providing me this opportunity to speak here in this event, the 9th Conference of Polish Society on Relativity. Today I am going to talk a little bit about ultracompact stars, which mainly about the gravastars in the light of minimal geometric deformation. Okay. First of all, I am going to explain about the gravitational decoupling. What is gravitational decoupling, which is introduced by the MGD. MGD stands for the minimal geometric deformation. Professor Wally, initially he proposed this idea in 2017 by the idea of introducing the gravitational decoupling by means of the MGD approach. In this approach, we consider one of the seed matter content, like we consider anisotropic, or you can say ideal perfect fluid. Then we introduce the new gravitational sources in terms of the energy moment tensor, like we opt new notation, like as given in equation number 1. We try to find out the T alpha beta tilde power n. N stands for the number of the new sources, and beta stands for the dimensionless coupling parameter. In this game, after combining the two different sources, we formulate the system of field equations. And to solve this system of field equations, we pick up the inner geometry that as given equation. You can see from the red side as we pick up the line element, and on the ingredients of the line element, we introduce a transformation as given equation number 2. In this transformation, the important thing is the coupling parameter beta, and there are two different unknown functions we can see from in equation number 2. It is k as a function of r, and there is h static as a function of r. Depending on the choice of these functions, we have two different approaches. Like first of all, initially we pick up the isotropic seed spacetime and the isotropic fluid, like we consider the perfect fluid. Then we will try to introduce the anisotropy in that case. In case of MGD approach, we have beta to be non-zero, and then h static is non-zero. But in this case, one of the functions for example, we pick up the k equal to 0. But if we choose that all these, both of these functions and also the coupling parameter, all these are non-zero, then we name it as the EMGD approach, which is called an extended MGD approach. In both approaches, we have calculated the mass function, then we can find out the gravitational redshift and also the observable proper time. To apply this approach, I have tried to pick one of the alternative theories of gravity, like apartheid theory. What is apartheid theory? Apartheid theory is one of the standard theory of Einstein's theory, in which we try to introduce non-minimal coupling between the scalar curvature r and the trace of energy momentum tensor capital T. In this case, the action of this theory is here given equation number 3, which involves the function depending on r and t. There is the Lm is the metal Lagrangian, and L stands for the Lagrangian density, which is introduced on the basis of the additional source phi per meter. And if we vary this action given equation number 3 with respect to the metric tensor g alpha beta, then one can find out the field equations as given equation number 4. You can see from in equation number 4 we have the Einstein tensor g alpha beta is the Einstein tensor, and the subscripts like capital R and capital T representing the partial derivative. Then there is also the covariant derivative is there, and there's the box function, the de-numbered operator is there, and if we substitute the seed matter source to be the ideal fluid or perfect fluid, in this case we can find out the field equations as given in this slide from equation 5 to 10. You can see from here there is the unknown function, capital so small f, and there is the fr and t, the derivative of the unknown function. So to apply this approach in different theories, we have to pick up the function, and to pick up the function FRT. Now there are different possibilities, but in this scheme I have picked up the very simplest case, like FRT is equal to r plus lambda t, which involves a minimal coupling between r and t. Why we pick up this model? Because if we choose a complex FRT functions, then in such case we find out that the new emerging sectors will be too complex to solve analytically. It's not possible to find an analytical solution, though we can opt to pick up the numerical scheme in this case. And second issue arises when we deal with the matching conditions across the boundary, that we have to match the interior and exterior of the spectrum. If we choose this model, then we can define the pure matter sector. You can see from equation 11 to 13, there is the contribution coming from the seed matter source, and also the contribution coming from the additional source, which is represented by this 500, 511, and 522. Okay, applying the transformation in case of beta static, beta delta equal to 0, and pure Einstein case, we can find the equations as given from equation 14 to equation 18. And in the second part of the equations, which we call the semi-Einstein equation or quasi-Einstein equation, and we can see from there we can calculate the value of 500, 511, and 522, which in terms of the unknown functions like a static is there. We have picked up the MGD approach, so we selected the k equal to 0. Okay, one more thing about this theory. In this theory, the important thing is the non-conserved energy tensor. We don't find the ideal conservation of the energy tensor as in case of Einstein's theory. So you can see from the equation number 22, the right hand side of the equation 22, there is lambda is a pair there. If we put up lambda equal to 0, we get the results of Einstein's theory. Depending on this case, there are so many models are developed to deal with this aspect in case of cosmology. Okay, in similar scenario, we can calculate the modified TOD equations, Tolman equation, as given in equation number 23. This formulation is appearing to the FRT theory. In the next slides, we define the total energy density, total rate pressure, and total tangential pressure to be like as given in equation number 24 to 26. Which involves the contribution from the seed source and also the contribution coming from the additional anisotropic source like 5001 and 22. Okay, another important aspect of this study, if we're studying the stellar object, then we have to see that what is inside the object and what is outside the object. So we have to the matching conditions. Space-time representing a compact object is divided by hypersurface. It divides the space-time into two distinct regions. One is called the interior region, and the other one is called the exterior region. The interior and exterior we must match both of these regions, and to match these regions, we opt the Israel matching conditions. These conditions provide us the continuity of the first fundamental form, which is depending on the contribution coming from the components of the metric tensor G00 and G11, the matching of the G00 and G11. Another one provides us depending on the response scalar, it helps us to divide the condition of the pressure, radial pressure at the boundary, and also we helps to calculate the mass function. Okay, to apply the MCD approach, we pick up the exterior spacetime, and if we deduce exterior spacetime and coming from the additional source, we call it the phi sector. In this case, if you see from equation number 27, there is an unknown function g static as a function of r. We will calculate this function. We just deduce this function just to show that this function will opt some external source from the deformed case, and capital N is the total mass in the exterior region. So from the continuity forms, we can formulate the relations as in equation 28 and 29, and in the first case, if we pick up that the additional external source phi alpha beta in the exterior region, phi alpha beta plus, you can see the plus sign, is non-zero, then we can formulate the phi 0, phi 1, 2, 2 in terms of the unknown function g static as a function of r. Now, to calculate this g static, and we have picked up the choice of the equation of state, depending on the definition of gravastar. The gravitational vacuum star, we call it the gravastar, which is proposed by Mazur and Motola, and it's as you can see, it's an interesting mathematical model for the description of extremely compact stable structures. And in this case, we have three different regions. If you see from here, if P is equal to -4, here you can see that there is an equation of state omega equal to -1. In cosmology, study of cosmology, you can see that the most famous model, we call it the lambda CDM model, omega equal to -1. Then there is omega equal to 1, by atomic fluid, and then in the outer region, in the vacuum case, we have both pressure and density to be 0. In this study, we pick up the first condition that we call it the dark range equation of state, which is omega equal to -1 for the interior of stellar system, which where r small r is less than equal to the boundary. And this condition P is equal to -4 helps us to calculate rho from the Q equation. We calculate it to be a fixed value, and then we can also calculate the pressure. Using all these parameters, we finally find out the undefined and undeformed metric functions as given in equation number 36 and 37. Okay, now if we calculate these unknown functions, then we have to think about the static which was reduced to represent the MCD approach. To calculate static, we consider the main characteristic of gravastar structure, which is just G00 and G inverse of G11. This is equal to 0 at the boundary. If we put up this condition, then we find out the expression for a static as given in equation number 38, where n is expected to be greater than equal to 2. And using this trial, we can calculate the E is for minus psi, and moreover, we try to apply the regularity condition in this scenario. The regularity condition helps us to calculate, to put up the additional constant on the coupling parameter, which is to be beta greater than equal to -1. Okay, the particular expressions for the rho total and the anisotropic factor and all these can be calculated. And let me explain about the deformed and deformed, difference between the two cases of the exterior and deformed and deformed. If we pick up the standard Schwarzschild solution where there is no contribution coming from the G static, then we pick up the beta to be equal to -12 pi, as a constant, and then there is also a regularity condition. And in this case, we can plot the total energy density, radial pressure, total radial pressure, depending on the choice of this parameter, and You can see from here the density is positive and the radial pressure is negative. And there is a line, there is a dashed line blue representing by the matching of the interior and exterior regions. And there is a Schwarzschild and which is shown in a black color. And similarly, in the second picture, we can pick up these parameters in a similar scenario. Okay, next one. Next one is the deformed Schwarzschild case. In this case, the outer space has received some contribution coming from the so-called so-called anisotropic sector, which is the additional source, the phi sector. In this case, D static is non-zero, and so we have to pick up some to calculate the D static. We have to pick up some conditions. So here we pick up that our additional source is traceless. We pick up this condition, additional source to be traceless. If we use this condition, then we can calculate the G static. G static as a function of R, as given in equation number 49. And using this value of G static, we can calculate the other metric components as given in equation number 50. And again, the second fundamental form helps us to calculate the unknown parameters. Like we can get the expression for L, which is appearing in this G static, and then we pick up the condition for we call it the regularity conditions, and which finally helps us to calculate the condition on the coupling parameter, which is lambda. We see that we need to have the lambda to be greater than equal to 0 to satisfy the regularity condition. Okay, in this paper we have shown the evolution of the interior as well as exterior radial component. You can see from here we have shown that in the Schwarzschild metric there is a black colored curve, and for the deformed Schwarzschild, which involves the contribution from the G static, we have the blue curve. It gets engineering gravastar. Now, finally, the expression for the state parameters in the deformed case, this can be evaluated as in following the similar scheme as we have shown in the previous case. Again, we have plotted it's showing almost a similar picture. There is a side difference of due to the deformed Schwarzschild case. You can see from here in this picture with the boundary term. The connection is showing the difference between the previous one and the new one. And here again we have plotted the total energy density and total pressure. Okay. Let me conclude my talk. In this case, we have introduced the anisotropic version of ultracompact stellar structure. For the Schwarzschild case, so we have the radius R is equal to 2m, which is tried to be developed in the scenario of for T3 of gravity, and we will put up the smoothly matching condition for the standard Schwarzschild solution. And for all cases, we have seen that it reduces the condition for a standard Schwarzschild solution. Lambda is greater than equal to 2 pi, the coupling parameter of the T3 gravity. And in the second case, for the deformed Schwarzschild solution, for the smooth matching of the interior and exterior, we have to pick up that lambda to be greater than equal to 0, but for the stable solutions, this condition leads us to pick up the constant from starting from 0 to 85. Okay, thank you so much.
Okay, well, thank you for your talk. So if there are any questions from audience, yes? We have one question. I hope you will be able to hear that.
can you hear me?
Yes.
Okay. So thanks for your talk. I'm just wondering something. So I understand that the solutions you obtain are smooth, so the metric is continuous, both the GDT and the GRR. But at some point, I think it was slide number 9, when you introduced the matching conditions, you mentioned that, yeah, if you could go back, please. Yeah, here, there. Yeah, so you mentioned that one of the requirements is the continuity of the first fundamental form, and that's basically the jump of the induced metric is 0, as you have written there. But my point is that the jump of the induced metric doesn't include the radial part of the metric. So you are imposing GRR to be continuous, which leads to solutions that are smooth, but that's an assumption that you're making. It's not necessary. Is that right? And I'm asking this because I believe that if you drop that assumption, so if you keep GDT continuous, but GRR, you allow GRR to be discontinuous, you can find more solutions than the ones you found. Because you mentioned gravastars have an interior plus a shell plus an exterior, and in your case, because you make this assumption, you don't have the thin shell, but you could have if you allow GRR to be discontinuous.
Okay, yes. I like this idea. Yes, if we try this approach, then we can find new solutions. I like this idea. Maybe I will try, but to keep the, can you hear me?
Yes, we can hear you.
To keep the stability of the exterior integers, that's why I will consider both of these conditions.
Yeah, okay, but it's just an assumption, right? It's not necessary.
Okay, thank you.
Yeah, thanks.
Any more questions? I can ask last one. So why is your black hole a radius of 2 kilometers? Is it just an example, or does it mean something?
You can say it's an example, not 2 kilometers. We don't know about this other factor. It cannot be 2 kilometers.
Okay, so I think there's no more questions, so thanks our speaker again.
Thank you.
Now we are going to the closing part of the conference. So thank you.
Yes, so this seems to be the last lecture, so let us thank the organizers and let us thank all the speakers.